the objective of interpolation essentially is given some n number of data and you want the independent variable value at certain other point which is not already covered by the data that is given to us, how can we get that value at the intermediate point. So the idea is to join the dots in a way where we have the data points, we will just join the dots and then find out the data value at one of the intermediate points within that data point. So that is the idea behind interpolation. So the first and straightforward method of doing interpolation is what we looked at in the previous lecture. We saw polynomial fitting. So if we had n data points, we said that we can fit up to n minus 1th order polynomial. So if we fit anything less than n minus 1th order polynomial, it's possible that some of the data will not be perfectly captured by the model. But if we have an n minus 1th order polynomial, when we have n data points with us, at that time that particular polynomial will perfectly capture all the data points. So the idea in interpolation or in extension of the polynomial regression to interpolation is that if we have n data points x1 y1 and so on up to xn yn, we in interpolation we need a method we are looking for a method to join the dots. Okay, that is what we are trying to do in interpolation. The straightforward extension of what we have learned so far is to fit an n minus 1th order polynomial. Okay. So the polynomial, the trial polynomial that we will try to fit will get the form y equal to a0 plus a1x plus a2x squared and so on up to not an, it will be an minus 1, I am sorry, x to the power n minus 1. So we have n unknowns a0, a1, a2 up to an minus 1. We have n unknowns and we will get n equations in n unknowns. The equations that we will get is going to be of the form d of sum of square errors. If sum of square errors is SE, just recollect what we have done in lecture 2 of this module. If SE is the sum of square errors, sum of square modeling errors y minus y hat, then the first equation is dSE by dA0 equal to 0, second equation dSE by dA1 equal to 0 and so on up to dSE by dAn minus 1 equal to 0. So we have n equations in n unknowns and there will be unique values of a0, a1, a2 up to an minus 1 that will give you a polynomial n minus 1th order polynomial fit to this data. Okay. And as we had done before, what we will write our y matrix as nothing but y1, y2 and so on up to yn. Our x matrix, if you recall, the first column of x matrix was 1 1 1 repeated n minus 1 times, that corresponded to a0. Then we would have x1, x2 up to xn which correspond to a1, so on up to x1 to the power n minus 1 up to xn to the power n minus 1. So this is how we will write. We will have this x1, x2 so on up to xn, and this is x1 to the power n minus 1 keep in mind we are fitting an n minus 1th order polynomial x2 to the power n minus 1 and so on up to xn to the power n minus 1. Just note that this particular n and this particular n are the same n's. We have n columns and n rows in the X matrix. As a result of this, our phi that we had written so far, we had written as x transpose x inverse x transpose y. That is what we had written our phi as. Now if X has this X matrix, this X is an n by n matrix. If rank of the matrix X is n, okay, then the rank of X transpose X is also equal to n. Okay, and we need the rank of X transpose X so that rank of X transpose X to be equal to n, so that X transpose X is going to be invertible. So if X is invertible and X transpose is X transpose is also invertible, and therefore X transpose X is going to be invertible, this we will be able to write this as X inverse X transpose inverse X transpose Y. Okay, keep in mind we are able to write this only because X is an n by n matrix. Okay, and that will give us really phi equal to X inverse Y. So you get this particular matrix X, just invert that matrix, multiply with the matrix Y, and we will be able to get the values of A0, A1 up to An minus 1. That will give us the perfect fit for the purpose of interpolation.